Question 1A. We're asked to calculate the average force exerted by the racket on the ball. So force is the change in momentum over the change in time. And so we have a mass, m, of 0.058 kilograms multiplied by a change in velocity, change in speed, of 64 minus 0. That's the correct way to write it. Divided by 25 milliseconds, which is 10 to the minus 3. So if we work that through, it's 148. If I just look at the sig figs, everything's to 2 sig figs, so I'm going to go ahead and do the same thing. Calculate the average power delivered to the ball. The issue that some people were having with this one is they didn't notice that it's average power. So where power is FV, what that actually means is the average V. So if your V is a constant value, then you just plug that number in. However, if like ours, you're actually going from 0 to 64, your average speed for the duration of the impact is half of that, so 32. So it's the mean value. So that's what we actually need to do. So I'm going to substitute in my calculation, 148, so that I'm not kind of making my number more and more out of whack. And then multiplied by, if I was to do it properly, what I would actually write is kind of 64 plus 0 divided by 2, which we all know is 32, but I'm just going to work it out properly. And then that works out as 4736, which again to 2 sig figs is 4700 watts. So lots of people had double that number because they didn't take into account that the speed was going from 0 to that value. They thought that the speed was constant. For question 1C, we're asked to calculate the time it takes the tennis ball to reach the net. So what I tend to do is draw my own little diagram. So even though we can't see the diagram, I'm going to draw my own little diagram up here with the information that I would like to keep. So I'm going to draw a distance to the net, which is 11.9 meters. I'm going to draw the net, obviously not to scale here, 0.910 meters. What else do I know? The initial speed, I know the initial speed is 64. Here's the ball. And I know that that's at an angle of 7 degrees to the horizontal. Right. So to work out the time taken to reach the net, it's actually distance equals speed times time. Because if we don't have any air resistance, and we would always discount air resistance unless we're told otherwise. then everything on the x-axis is staying the same. So we're trying to find the time taken. Sorry, I'm struggling with my pen, hold on. So we know that we're trying to find t, so S over V equals t. So S is 11.9 meters. So I'm really struggling with my pen, hold on. Right, I'll try to make the screen a bit smaller to help. Divided by the horizontal. Now we can work out the horizontal like this. So we know that if this is 64 and that's 7, then this is the initial horizontal, which is 64 cos 7. So therefore, T equals 0.187, which to 2 sig figs is 0.19 seconds. Show that the tennis ball passes over the net. All right, so we know that the vertical speed is 64 sine 7. So if we work that through, we get 7.8 meters per second. Now we know that it takes 0.19 seconds to reach the net. So if we say it's falling at an initial speed of 7.8 and then it's just going to accelerate down with gravity, if its initial speed is 7.8, what we can do is we can work it through and we can say, well, what distance is it going to cover in 0.19 seconds, falling at a rate of 9.81 meters per second squared? So I'm going to use the vertical S equals ut plus half at squared, and I'm going to sub in, so SV, so we can say, well, we don't know this one, so how far is it going to fall? And so ut, so that's going to be 7.8, this uv here, multiplied by 0.19, plus, because it's falling with gravity, half times 9.81 times t squared, and we can work out the distance it will fall, and the distance it's going to fall is 1.659 meters. All right, so 1.659 is the magic number. Now we know that, I'm going to color this in pink. All right, so we know that it starts off at 2.8 and we know it falls 1.659. All right, so here's 2.80, it falls 1.659. So the question is, has it fallen too far? Is it going to be lower than 0.91, in which case it won't go over the net, or is 2.8 minus the distance it's fallen still higher than 0.91? And indeed, if we work that through, if we say 2.8 minus it's fallen 1.659. By the time it hits the net, it is at 1.14 meters, which is greater than 0.10. So it's going to miss the net. It's going to fly straight over. I'll go back to blue now. Determine the speed of the tennis ball as it strikes the ground. That means what is the resultant speed. So what it's saying to you is it has a horizontal speed, it has a vertical speed, and it's saying, please can you work out the resultant. So you just need a bit of Pythag, really. So the resultant speed equals the square root of vh squared plus v squared. And we need to know what vv is. So v squared equals u squared plus 2as. v squared equals u squared plus 2as. So by the time it has fallen 2.80 times by g times by 2 plus its initial speed, which was 7.8 squared. Its final speed squared is 115.776. So its final speed is the square root of that, which is 10.76. So it's 10.76 here plus the horizontal speed, which was 64 cos 7, which was 63.52. Squared. So it's a little bit messy now, isn't it? So final speed is 64.4. There we go. For 1F, a lot of people got 1 mark. Right, so we are told that the normal reaction force is the same for both surfaces. If the normal reaction force is the same, I'm just going to write this. If the normal reaction force is the same, that means the vertical component of V is the same. Not the horizontal, but the vertical. All right. So what we have is, let's say we've got grass. And clay. And we've got a vertical like that. And we know that if the normal reaction force is the same, then the vertical component of V is going to be the same. But we've got friction is greater for clay than the grass. So the force of friction for clay is greater than that of grass. And that means that the horizontal speed for clay will be less than for grass because it's slowing it down. It's acting against it. So for clay, we might have something like this, whereas for grass, we might have something like this. And so we can see that the resultant here, so this angle here for clay compared to this angle here for grass, it's going to be larger. All right, and that's why. Okay. Question 2 is a sample of gas, and it starts off asking us to estimate the average speed of helium atoms in a container. So average speed comes from kinetic energy, and kinetic energy is half mv squared. Now, kinetic energy of an ideal gas is also 3/2 kT. Now, given that we're looking at temperature and we're looking at mass and we're looking at speed, we're going to need to equate these together. So K is Boltzmann's constant, 1.38. Let me write that down. Times 10 to the minus 23. You can find that in your formula booklet. And then what we're going to do is we're going to rearrange for V. So V squared equals 3 kT over m. Therefore, V equals 3 kT over m, and that's going to be the square root. So V, if you substitute in all those numbers, you get 1.4 times 10 to the 3 meters per second. Show that the number of helium atoms in the container is 4 times 10 to the 20. This one wasn't done particularly well, actually. Now, there's different ways of doing this. I like to use the PV equals nRT formula, but I know that other people are more familiar with NKT. So I'm going to go ahead and do the PV equals nRT. And I don't think this one is in the formula booklet. But what I can do, so N is the number of moles. All right, so N is the number of moles. I'm well aware that we need the number of atoms. Okay, so this is the number of moles. So what I'm going to do is go ahead and rearrange. Now R is 8.31, and if I rearrange for N, what we do, we always show our working for IB. There's marks in that. You don't get full marks for a bald answer much of the time. So you really have to do this. Big difference to GCSE. Don't waste marks by not showing your working. You just can't afford to have forced errors like that. So that is the number of moles, which is like packets of a certain number of particles. It's like baskets of, like full baskets of particles. Right, the number of moles is the number of particles divided by Avogadro's constant. So Avogadro's constant, and I'm very happy to spend some time with anybody that struggles with this. Avogadro's constant says that Na is this quantity of particles, molecules, if you will, atoms. All right. Particles, molecules, atoms, we don't really differentiate in physics. We leave that to the chemists. Okay. So Na is Avogadro's constant, and that is a certain number of particles. That does not change. So if I say I've got Avogadro's constant worth of helium, I have this many particles of helium. If I've got Avogadro's constant worth of, I don't know, fluorine, then I have this many particles of fluorine, right? N is the number of particles I actually have. So, for example, if I had 12.04 times 10 to the 23 particles in real life, if I divide that by Avogadro's constant, you might be able to recognize that that divided by that is going to be 2. So that means I've got 2 moles. Basically, the number of moles is how many lots of Avogadro's constant do I have. All right. So I have this many lots of Avogadro's constant. So if I rearrange for n, which is the number of atoms that I want, it's, sorry, I've got this many moles, this many lots of Avogadro's constant, times by the number of particles in Avogadro's constant, and that equals 3.7 times 10 to the 20 particles now, or atoms. Now remember, because it's a show that, you have to put at least one more sig fig. If you're being smart about you put 2 more. All right, you have to go more than one sig fig if it's a show that. All right, so when you're reading a question, as soon as you see that word or 2 words, show that, like underline it, highlight it, asterisk it, whatever you need to do, because once you get into the calculation, you might forget at the last point to do that. 2c, a helium atom has a volume of 4.9 times 10 to the minus 31. Calculate the ratio of the number of atoms to the ratio of, to the volume of the gas. So we have one helium atom. So that's how much space one helium atom takes up, but we don't have one. We have this many. So we have to multiply. All right. And that's why it's a show that. If you get a show that, it's probably going to be needed, that number, 4 times 10 to the 20, is probably going to be needed in the next question. So if you're not using that number in the next question, you're probably missing something. They put it there because you're going to need it in the next question. And if you don't get the answer right, like 3.7 times 10 to the 20, you could still use the 4 times 10 to the 20. And then we need to divide it by the volume of the helium gas. So what was the volume of the helium gas? Right up at the top, 3.2 times 10 to the negative 6. And that's 6 times 10 to the 5, make negative 5. No units because it's a ratio. Discuss by reference to the kinetic model of an ideal gas and the answer to C whether the assumption that helium behaves as an ideal gas is justified. All right, so they're looking for you to discuss about whether something to do with volume of atoms in a gas. So you have to kind of dig into your recall of the different assumptions for an ideal gas. There's several of them. And you have to pull out the one that is relevant to volume of atoms in a gas. So the relevant one is volume of an ideal gas particle is negligible compared to the volume of an ideal gas. Okay. So question C shows, all right, that the particle volume is far smaller, or something like that. So it's true. Yeah, because it's 6 times 10 to the minus 5 times smaller. So what's that? Like 100,000, 600,000 times smaller, something like that. All right. So yeah, it agrees. Question 3A. A lot of people here talked about how a standing wave is formed. All right, so a lot of good definitions were lovely, but they were about how a standing wave is formed. It wasn't the principle of superposition of waves. The principle of superposition of waves is that when two waves meet, the resultant displacement is the vector sum of their individual displacements. So I'm just going to pause the video and then write that down for you. So when two waves meet, the resultant displacement is the vector sum of their individual displacements. 3B, we have a double slit. So I'm going to go ahead and note this down. So the distance from slit to screen is capital D, and the slit separation is little d. And then the distance between fringes, like here and here, for example, is S. So the distance between successive maxima, kind of fringes if you like, is 4.7 millimeters, it says. So it's 4.7 times 10 to the negative 3 meters. Have I missed anything else? No. All right, so calculate the wavelength of the light. So SD over capital D equals lambda. And the only thing I need to watch out for is different units. So I've got 4.7 times 10 to the minus 3, that's S, multiplied by little d. I'm going to watch out for the units here because I'm in millimeters, need to convert. And I'm going to divide that through by the slit to screen length. It's 2.4, which creates 6.85 times 10 to the minus 7, but it says to an appropriate number of sig figs. Some people missed this, so I'm just going to go ahead and see what I need to do it to. 2 sig figs. So for that final mark, it needs to be 2 sig figs. What am I working in? Meters. Right. 3C. Explain the change to the appearance of the interference pattern when the red light laser is replaced by one that emits green light. So we are looking for the appearance. So appearance, I'm going to go back to the formula. When they're talking about the appearance, the only thing out of this formula is the slit width. Sorry, not the slit width, beg your pardon. The distance between successive maxima, the fringe separation. So what we can do is we can look and see what happens. So we've got a long wavelength for red, and then we've got a shorter, I'll call it a short, wavelength for green. So So I would say something like wavelength of green is shorter than red. Therefore, so if this is getting smaller, then they're getting closer together. Therefore, the distance between successive maxima decreases. They're getting close together. And you might be able to kind of visualize that in your mind from when you've done it in class, when we've had a red laser pen and then a green laser pen, and we've actually had a look, and you see that the green ones get very close together and the red ones are much further apart. If you can't picture it, it would be worth asking your teacher to go through that with you again, just getting a couple of laser pens and just seeing them through them. 3D, one of the slits is now covered. So we're going from a double slit to a single slit pattern. And you need to know the difference between them. So this is that. The central maximum will be brighter. So the central maximum will be bright, and then the maxima either side will be dimmer. All right, so the central maximum stands out with dim maxima either side. The other thing to note is that the width of the central maximum is twice that of the secondary maximum. Width of central maximum equals 2 times the width of the secondary maxima. And it comes from that graph. I'm not going to do this justice, but if you've got like that, yeah, and we've got something like that. So this distance and this distance is the same, but remember that distance is actually only half of that, so to speak. Question 4 is about electricity. All of it is. So we're going to start with potential difference across. So we've got 4 resistors. All right. So we've got P, Q, and R, which are all fixed resistors of different values. And then we've got a variable resistor, S, made from conducting putty. You can reshape it. So to me, that is alarm bells, that we're going to potentially have something to do with kind of this kind of thing. If we can reshape a resistor, it could be that something like that is going to come up, if not in this part of the question, or maybe later on, something like that. Okay, so we are asked to find the potential difference across P. So we have, let me just look at it. I'm just going to look at this for a second and pause it. Just bear with me. Right, okay, I've got my head around it. Okay, so we've got conventional current going through here like that. This conventional current is either going to take the first option or the second option. So the current's going to split. Now, if we focus on the PR section, we can say that because these are in series, kind of the voltage across P and R, all right, so P and R junction. So this PR junction here has 6 volts across it. Now, I'm only going to look at that for now. There's no need to incorporate Q and S. So we have 6 volts coming in. And that's like that. If we've got 6 volts, then they're shared between those. And we know that the ratio of the sharing of the voltages is equal to the ratio of the resistors. Okay, so if you like, you could say V P equals, VP over resistance P, the voltage over the resistance equals the voltage total divided by the resistance total. Therefore, VP equals V total times by RP divided by R total, because it's all to do with ratios. So VP equals the total voltage across P and R section is 6 multiplied by the resistance of P, which is 40, divided by the total resistance across the 6 volts. They're in series, so we just add them. So it's 100, and that equals 2.4 volts. So the voltage across P in that situation is 2.4. The voltmeter in their diagram reads 0. Determine the resistance of S. Right, so I'm just going to remove this voltmeter that I've put in. So this one here reads 0. Now, if that reads 0, then we have 2.4 volts across Q. So it's saying that if we've got 2.4 volts in this bit, and the difference between the voltage of P and the voltage of Q is 0, then this must be 2.4 as well. So if V equals 0, then the voltage across P must equal the voltage across Q. So we know that if 2.4 volts is going through Q, then we can work out how much voltage is going through S. So the voltage through S is the 6 volts traveling through minus the 2.4, the voltage through Q, and that's 3.6 volts. Now we need to know the resistance of S, which is the one that's in line with Q. So we need to know the resistance. So it's saying, what is the resistance here? What is the resistance? So if we know what the voltage is, we're trying to find the resistance, we just need to work out the current. So the current through Q is V divided by R, again, both for Q. We have all these numbers, we just need to plug them in. So it's 2.4 volts divided by 16 ohms equals 0.15 amps. So we've got 0.15 amps passing through resistor S. So resistor S equals V over I. 3.6 divided by 0.15, 24 ohms. 4C, we've got the resistivity question coming in. All the putty is reshaped into a solid cylinder that is 4 times longer than the original length. Right. So we've got a piece of putty that has been stretched. So, well, it's got a volume of pi r squared L. So here is pi r squared, and this is L. So it has a volume of that. Now this putty, it must have the same volume. You can't change the volume unless you're actually adding or removing putty, but we're not. We're just reshaping it. So the volume is going to be constant. But this time it's having 4L. So if the length is 4 times bigger, the area must be 4 times smaller. So we need to know what happens to the new resistance. So we have this. What happens to the new resistance? Well, the resistivity is to do with the material. It's not the dimensions. The dimensions is to do with the resistance, and the resistivity is to do with the material. It's non-dimensional. So the new resistance equals 4 times longer divided by A over 4. So that shoots up to the top. So the new R is 16 times bigger. It's 4 by 4 times bigger. So it was 24 ohms. It's now 16 times bigger. Punch that into your calculator. 384. I'm going to stick with 2 sig figs. 380 or 384. I'd leave both numbers in there. 4D. Outline without calculation, right? No numbers here. Change in the total power dissipated in Q and the new cylinder after it's been reshaped. All right, so power dissipated is I squared R. So we know that we have now increased the resistance. So we've increased the resistance, but if the area has reduced and the length has increased, the current also reduces. So as the power is proportional to I squared, the power also decreases. Five A, define gravitational field strength. It's one of those recall ones. It's an easy mark to grab, so please take it. It's yours for the taking. G is the gravitational force per unit mass on a test mass. Gravitational force per unit mass on a test mass. State the SI unit for gravitational field strength. That's a nasty one. It's a bit of a trick. It's actually newtons per kilogram. It's not meters per second squared, I'm afraid, which a lot of people wrote. I know newtons is not an SI unit. Hopefully you are screaming that through YouTube at me right now. I know that, but the SI unit for gravitational field strength is in fact newtons per kilogram. It's a weird one. That's just how it is. It's not a base unit, but it is the standard unit for gravitational field strength. Please don't get caught out. It is not meters per second squared. You wouldn't say the value of gravity is 9.8 meters per second squared. We don't do that. It's 9.8 newtons per kilogram. 5b, a planet orbits in a circular orbit with orbital period capital T and orbital radius capital R. The mass of the sun is m. Show that. Now, a lot of people didn't go right back to basics here. A lot of people jumped straight through to something where they pulled out 4 pi something. Certainly if you were marked by me, you didn't get both marks because you didn't go back to basics, okay? You have to show where it's come from. You can't just pluck things out of kind of thin air. So what we expected you to do was to say that the gravitational force is gmm over r squared. And you were expected to recognize that that is equal to mv squared over r in a circular orbit. You had to start there, all right? We can cancel the little m's and we can cancel an r. So we can say that gm over r equals v squared. Now, I know where your 4 pi squared bit came from, but you didn't show that, okay? So v, what is v? V is the kind of speed of orbit, which is that. Now we want v squared, 4 pi squared r squared over t squared. So what I'm going to do is say gm over r equals 4 pi squared r squared over t squared. Cancel, cancel. Is there anything else I need to do? No. And now I'm going to rearrange. Sorry, didn't mean to do that. I shouldn't have done that. Can't do that. That needs to go up there. Beg your pardon. Therefore, t equals 4 pi squared r cubed over gm square rooted. There you go. You have to work hard for those 2 marks. Estimate the mass of the sun if the Earth's orbit, so the distance of the Earth around the sun, is 1.5 times 10 to the 11 meters. So the Earth's orbit around the sun. So again, it was a show that. So we're going to need to use it later on. So a show that question, chances are you're going to need to use the answer in a later question. Okay, so We're trying to find M. Right, T. T squared is the time taken for one orbit around the sun, because we are dealing with an orbit around the sun. All right, so it's not one day, it's not 1 week, it's not 1 month, it's a year. So it's 365. I must be honest, I always do 0.25, but I don't think the mark scheme wanted that. I can't remember. I think they were happy with 365. And I've squared it because it's t squared in the equation. So that number, you'd be sensible to write out what that works out as, but I won't do. 4 pi squared times by 1.5. This is the radius going in here, divided by 6.63 times 10 to the minus 11. Yeah, equals m. And m is a number you should be fairly familiar with, which is approximately 2. Right, you should have that knowledge that the mass of the sun is 10 to the 30. Really. 6a, state what is meant by the binding energy of a nucleus. The binding energy of a nucleus, now there's different ways of learning this. You can either talk about the energy required to separate, or you can say the energy released when you bring together. I like to say when you're separating. So I always say it's the energy required to separate the nucleons of a nucleus into their constituent parts. 6b wasn't done particularly well, actually. It was the binding energy curve. So you should be aware that the most stable atom is iron, which is 56, I think. So you want it to peak around here. So it grows and then it tails off. And you can, so this point here is the point of maximum stability. Apologies if I've got that number wrong. It's iron. Wherever iron is, the mass number of iron, I think it's 56, but I could be wrong. But yeah. So what that means is anything kind of in this direction after the highest point, this needs to be the highest point, basically. Energy is released by fission, and anything in this direction, energy is released by fusion. We've now got what have we got? An alpha decay, and we're looking for the energy released. So we've got plutonium 238, and that is going to uranium 234 plus a 4 to alpha. How did I know that uranium is 234? Well, I know that it's released by alpha. It's alpha decay, and alpha is 42. So 238 goes to question mark plus 4. What plus 4 equals 238 is 234. I don't need to worry about the atomic numbers. And I need to know the energy released. So I need to know, now these are per nucleon. So I need to know how much energy, kind of what is the energy for plutonium, what is the energy for uranium, and what is the energy for the alpha particle. And then what we say is the energy of the uranium plus the alpha particle, there will be a difference between that sum and the sum of the plutonium. This sum will be bigger, which means that there'll be an energy released. So I've got 238 nucleons of plutonium, and each one has 7.568 mega electron volts, which is 1/8. You have to work to so many decimal places on here. Okay, please don't take shortcuts. And then we've got, I'm going to do this in one go, 234 by 7.6 plus, that was a bit northern, wasn't it? 4 times 7.074. Okay, so those together equal 1806.696. Okay, so this number is higher than this number. So the difference in energy equals 5.5 mega electron volts, and that is how much is released. Calculate the ratio of the kinetic energy of the alpha particle compared to the kinetic energy of the uranium. So, kinetic energy, this is actually, so we've got kinetic energy of alpha divided by kinetic energy of uranium. Now, we can't necessarily do this through kind of a speed, but we are given enough to do this through momentum, and I'll show you how. Now, we know that kinetic energy, pretty sure this is in your formula booklet, is that. So the kinetic energy of a particle is equal to the momentum squared divided by 2m. All right, so we have a plutonium nucleus at rest, and then it decays. So the how can I put this? The momentum of the uranium will equal the momentum of the alpha particle. The momentum of the uranium will equal the momentum of the alpha particle. So I'm just going to write that. Momentum of uranium equals the momentum of the alpha particle. So what I'm going to do, I'm just going to box that off actually. So I'm going to plug in p squared over 2m for alpha, and then divide that by p squared over 2m of uranium. So we've got p squared alpha divided by 2m alpha divided by kinetic energy of uranium, p squared uranium divided by 2 mass uranium. So I was taught at school, if you're dividing by a fraction, you turn it upside down and multiply. So I'm going to go with p squared alpha over 2m alpha multiplied by an upside down fraction. I'm going to put that in brackets just to show you. Like that. And this is equal to this, so they cancel. Sorry, didn't mean to do that. I'm getting carried away with myself. this is equal to that. So we've got, the ratio is, oh, we've got a 2 and a 2. So it's mu, so it's mu over m alpha. So it's 234. After all that, 234 over 4. It's just the ratio of the inverse of the masses, which is 58.5. That was quite hard, that one, I think. (7A), you if you didn't get full marks for this, a lot of you had a really good go at trying. So hats off to you. I think you were getting the right idea. Right. If we've got a sphere, I can't draw a sphere. I can't draw to save my life, but as you guys know. But let's say we've got a sphere. All right, and just go with me on this one. Just humor our physics teacher. Right, so say we've got a sphere. When the sun strikes, here's the sun. When the sun strikes kind of a portion of kind of a sphere or something like that, it illuminates a flat cross section. All right, so it's a flat cross section. And so whilst the surface area of a sphere is 4 pi r squared, the cross section that is illuminated is just pi r squared. It's not a sphere, it's just a flat section that's illuminated. And that's where this quarter has come in. So what did you have to do for the marks? You had to firstly kind of say what this whole PA divided by A type idea comes from. So I would have said the intensity, if you like, equals the power over the area. So for a sphere, area equals 4 pi r squared, or d squared, because it will illuminate kind of over this distance. All right. So for a sphere that's distance d away, it will illuminate 4 pi. It will cover a region of 4 pi d squared, a bit like blowing up a balloon. The more you blow up a balloon, the bigger the sphere is getting. A bit like that. So that's kind of the first idea. But where does this a over 4 come from? Well, this is what I would write. The light strikes as a cross-sectional area. You know, normal, that's a good way of saying it. Normal to the sun's or the solar radiation. So 4 pi d squared needs to be divided by 4 for cross section. As I say, even if you didn't get your 2 marks, you had a really good go at it. Right, 7b, we were looking at albedo. So albedo, first of all, is the total scattered by P . So it's the total scattered power divided by the total incident power. Now we know that power equals E sigma A T to the fourth. So we know that P equals, I'm going to plug in here, 4 pi d squared. D squared E sigma T to the fourth. So I've done a theta there. All right. Now, we know, what's the best way to explain this? Okay. We know that the power absorbed is P1 minus alpha. All right. So the total scattered, the amount scattered out of 1 is, so let's say, for example, that the albedo is 0.1. That means that 0.1, so 10% of the total amount that's incident is going to be scattered. So if we said 100 minus 10%, 100% minus 10%, or like, for example, 1 minus 0.1, so 0.9 is the amount absorbed. So that's where that's come from. All right. So we're saying if that is that, I think I've taken a bit of a shortcut there in my head, then 1 minus alpha P equals kind of the total absorbed. But we need it as a quantity of power, like that. Okay, right. So we know that, I'm going back to this bit now. We know that that is that, but we also need to times this by kind of A over 4. So a quarter of that. So we've got, I'm going to, shall I rearrange? I'm going to try and do all of this in one go, okay? Let's see how I get on. So we've got, I'm going to rearrange for t to the fourth. Okay, and just pause a second so that you can see where this has gone, like that. All right, just going to pause a second. And then I'm going to say, well, actually, I only want a quarter of it because we've gone from a spherical area to a cross-sectional area. And then that would be for the amount, scattered. We want the amount absorbed, so I need to switch that in for 1 minus alpha power. Okay, so again, this was a really hard one, and I don't think I probably explained that as clearly as I might have done. So if anybody wants to come to me and I can work through it again a bit better, it's not very easy when you're recording and you're trying to think on your feet and stuff. But yeah, apologies for that. Okay, very happy to explain that any other time. So if you're stuck with 7b, just come and find me. Calculate the surface temperature of the moon. So I'm just going to pull in the previous formula and we're going to plug in. So we're talking about the moon this time instead of a planet. So 16 pi d squared E sigma. Now sigma is Stefan's constant. I love it. It's one of my favorites. It's just 5.678. Love it. 5678. Don't forget the negative sign. So t is the fourth root of the solar constant. So the solar constant, if you're not sure, the solar constant is that. All right, I think that's in your formula booklet. So that's the solar constant. So we can see that the solar constant here is S. So we've got 16 and 4, so we've still got a factor of 4, like that. Okay. So we've got fourth root, the solar constant, multiplied by 1 minus the albedo, 0.13. So that's saying 13% is scattered. Divided by 4 times the emissivity, which is 1, times by Stefan's constant, 5, 6, 7, 8, negative. So if you do the fourth root, don't forget the fourth root, you get 269 Kelvin. So 2 sig figs, 270. Question 8, we have a small metal pendulum bob that's suspended from a length of thread. The mass, then the thread has no mass. The pendulum starts oscillating, and we have a kinetic energy time graph. Note that this is kinetic energy. A lot of you fell into the trap. You didn't look at the axes. Calculate the length of the thread. So the length of the thread, you're given everything you need to calculate it. We are trying to find the length. I have just done a little leap of faith there. Is the length. So T is not 1.25 because it's kinetic energy. It's not amplitude, it's kinetic energy. So we're starting from maximum kinetic energy. So here is kind of equilibrium. Let's say equilibrium, and then it goes to maximum left point. Then it goes to equilibrium, maximum right point, and then back to equilibrium here. So this is the start. Sorry. This is the start of an oscillation, and this is the end of an oscillation. A lot of you didn't check the axis. So it's 2.25 seconds. So the length is t squared times by 9.81 divided by 4 pi squared, which equals 1.26 meters. Oh, actually it says an appropriate number of sig figs. What am I going to go for? 2 sig figs. Okay. 8b, label on the graph with the letter X a point where the speed of the pendulum is half that of its initial speed. Again, you might not have looked at the axes. So we need to know what happens to speed if you halve the kinetic energy. Oh, sorry, hang on. What happens to the kinetic energy when you halve the speed? So kinetic energy, if you look in your data booklet, we've got this scary looking formula. Okay, and the point you need to take away is that EK is proportional to omega squared. So what happens if we do omega over 2 squared? That goes to omega squared over 4. Okay, so omega squared over 4, which means this divides by 4. So we were looking at a point where the kinetic energy reduces by 3/4. So here would be a good point. The mass of the bob is 75 grams. Be careful, they've put it in grams. Show that the maximum speed of the bob is about 0.7. So kinetic energy is half mv squared. So we are trying to find V max. So V squared equals 2ke over m. But I'm just going to actually scrub out the square and do a square root. So maximum speed is going to be where the kinetic energy is maximum. So we've got 20 millijoules. Be careful. So it's 2 times 20 times 10 to the minus 3 divided by, I'm going to put that square root in there because I'm very good at forgetting them, 75 times 10 to the minus 3, which works out as 0.73. Let's just show that. So I'm going to go with a couple more sig figs. Why not? Let's go mad. Okay. When the 75-gram bob is moving horizontally at 0.8, it collides with a small stationary object, also of mass 75 grams. The object and bob stick together. Okay. Calculate the speed of the combined masses immediately after the collision. It's 0.4. All right. I will show you how to do it, being the kind, lovely soul that I am. However, alarm bells really should be ringing because you've got a stationary object, 75 grams. You have a bob, 75 grams. This has a speed of 0.8. This has a speed of 0. When the bob collides with the object, the mass, they stick together. So the mass, so we know that initial momentum equals final momentum. So the initial momentum comes from Mr. Bob here, or Mrs. Bob. So we've got, I'm not going to worry about units right now. So we've got 75 times 0.8. All right. The object has no momentum because it's not moving. However, the final momentum comes from 150 lots of speed because the bob and the object are joined. They stick together. So we've got double the mass. You're going to halve the speed. Okay. Show that the collision is inelastic. Inelastic is where the kinetic energy after is less than the kinetic energy before. So we are expecting for a loss in kinetic energy. So the kinetic energy before, remember this is scalar, so we're just looking for magnitudes here. The kinetic energy before, which is half mv squared, we've got half times the mass of the bob, I'm going to put it into kilograms, times by the speed of the bob squared, which is 0.024 joules. The kinetic energy after is half times the bob and the object times by their speed, which is why it was was it a show that question? No, it wasn't a show that question. Right, okay. All right, which is 0.012 joules, which is quite handy actually, because you can see that we've lost half of the amount. All right, so we've had a 50% kinetic energy loss. Therefore, it's inelastic. F, sketch on the axes a graph to show the variation of gravitational potential energy with time for the bob and the object after the collision. Okay, if we're after the collision, then we have lost half of the energy. Yeah, we've lost half the energy. All right, so after the collision, we are traveling at kind of half the speed. We're moving double the mass, we're moving at half the speed. So we've lost half the energy, which means that not only is it going to be inverse as gravitational and kinetic are, but the amplitude is not going to go up. So if this is kind of 0, 1, 2, 1, 2, it's going to go from here up to here, like this. A bit like that. Okay. So we're going to have half the amplitude, and we're going to kind of be the inverse. (9a), the diagram shows the electric field lines of a positively charged conducting sphere of radius r and charge q. Points A and B are located on the same field line. Explain why the electric potential decreases from A to B. All right, well, we've got a positive conducting sphere here because we can see the field lines go kind of out. So they always go from positive to try and find a negative. So so we have a positive electric potential because it's KQ and Q is positive divided by R. So as R increases, V decreases, first of all. That would be in the numbers, in the formula. But as V is positive, because Q is positive, the V becomes less positive. Draw on the axis variation of electric potential with distance from the center of the sphere. So V is proportional to 1 over R. So we need a 1 over R law. Must be honest, I'm not the best at drawing these. But you are, because you've had lots of practice in your revision. So it's something like that. Might be a bit steep. And then inside, it's a constant value. So it's constant at that value. Doesn't go up, doesn't go down, it's constant. Nine C. Calculate the electric potential difference between points A and B. So we've got point A. So the electric potential for A, and then the, so hang on, let me just draw this. A is 5, so I'm scribbling my pen again. A is 5 times 10 to the minus 2, and B is at 1.01 times 10 to the minus 1. Okay, so we're going from the difference, A minus B. So we've got KQ over R minus KQ. K is 8.99 times 10 to the 9, 1.01. 1.1 times 10 to the 3. So, therefore, Q equals 1.2 times 10 to the minus 8 coulombs. I have missed out a step there, but hopefully you can kind of work through and figure out what I've done by plugging in the numbers accordingly into your calculator. Oh, apologies, I've just done 9D. I was copying it from my working, and I've just done 9D there. What a donut. Right, apologies. That is 9D. And 9C. Right, sorry. Right, so this is 9C, this is 9D. Right, try again. So calculate the electric potential difference. Right. Yeah, I was trying to figure out where I'd got that number from in my working. That's actually the answer to 9C. So 9C, we are now going to calculate 1.1 times 10 to the 3 volts. So V is the work done divided by the charge, which is 1.7 times 10 to the minus 16 joules divided by the charge, which is 1.6 times 10 to the minus 19 coulombs, which, believe it or not, is that. Okay, right. And then we know that the electric potential difference is this minus this. So that comes, potential difference equals KQ over R minus KQ over R. Yeah, plug all that in, rearrange for Q, and you get Q equals 1.2 times 10 to the minus 8. I'm really sorry, guys, for getting that all screwed up. 9E, the concept of potential is also used in the context of gravitational fields. Suggest why they developed a common terminology. If you've got a common terminology, it's generally because there are similarities. And I think actually that's the wording in the actual mark scheme, but it'll be similarities between different kind of situations of the same thing. So we are talking about fields, between different fields. Beg your pardon. Okay, so it's to do with similarities. That's why we develop common terminology. Calculate the current output by the transformer to the grid. Give your answer to an appropriate number of sig figs. Right, before you listen to this, please just have a read through 10A. There is a lot of information there, and I'm just going to go straight through to the working. So we know that the transformer has an efficiency of 96%. So 96% of the power in becomes the power out. In other words, 96% of current times voltage in becomes the current times the voltage out. Right. So if I want to know what the current output is, I'm going to go 0.96, 96%, times by my output current to the transformer, which is actually my in, times by my voltage into the transformer. Okay, so these ones are the in. This one is the out. And then I divide that by my voltage out, so it's just 330,000. And I get 284. So I'm going to go to 2 sig figs, because I like 2 sig figs. So does IB generally. And that's your answer. It wasn't quite as tricky as some people thought it might have been. Identify the main advantage of using a very high potential difference. Right, so we know that power loss, this is actually a GCSE idea. I'm not saying it's easy by any means, but we do teach it at GCSE when we're teaching transformers in the national grid and the high voltage power lines. So power loss comes from I squared R. So if V is very high, then I is very low for a given P. And what I mean by that is P equals IV. So for a given value of P, if we make this one super duper high, we can make this one low to get a certain value of P, which is great. Because P is proportional to I squared. Power loss, I should say. Power loss is proportional to I squared. So keep that I low, keep that V nice and high. In an alternating current, an AC generator, we've got a square coil rotating in a magnetic field. Explain, this question was not done very well. 3 marks, it was yours for the taking. Explain with reference to the diagram how the rotation of the generator produces an EMF between the brushes. Now, a lot of people wrote, if you look at your answer and then you look at the mark scheme when you're listening to this, you'll probably be thinking that's what I wrote. It's not. Firstly, you weren't writing in IB language, you were writing in GCSE language. And secondly, you weren't going into the right level of detail for IB. So yes, you knew what you were talking about to a certain level. You understood the basics. Did you use the correct terminology? No. And did you go to the correct level of kind of explanation, like going because, therefore, we didn't get the correct number of steps. You were kind of adding more and more detail to a single point. We needed 3 separate points, like a flow diagram, like a proper story of how it works. So, in IB language, the lines of flux, not field lines, are cut by AB and CD coil lengths. Not the field lines are cut by the wire. All right, that isn't the same thing. Well, it kind of is, but that's more GCSE. So the field lines, the lines of flux, are cut by the wire lengths AB and CD. Not BC, not AD. All right, nice and crisp and specific, please. I don't know if you can hear my dog whining in the background. The EMF depends on the rate of change of flux. Throw in that formula in words. So, an alternating EMF, read the question, we want an alternating EMF, is induced as AB and CD are in the same direction wrapped around the coil. Okay. Calculate for the position in the diagram the magnitude of EMF generated by a single wire. It's even in bold. It's even in bold. Right. EMF equals BVL. So we have a magnetic field strength of 0.34 Tesla. We have a speed of the edge, AB, of 2 meters per second, and a length of 8.5 centimeters. Okay, centimeters, not meters. We don't want 80 wires, we want a single wire. So please don't multiply it by 80. It was even in bold. How kind was I? Okay, I'm going to say 2 sig figs for this one, I think is appropriate. Hence, calculate the total instantaneous. So we've got 80 kind of what turns. I was about to say wires. Sorry, I think I said wires in the previous question. Turns moving up, and we have 80 turns moving down at the same time. So if you add them together, we have a total of 160 turns of movement, cuttings, if you like. So we've got 160 by the EMF, which equals 9.28. So I'm going to go to 2 sig figs again. Peak EMF is 9.3 volts.